and welcome everybody to another of our almost weekly CCPO and ICAR seminar series. It's my great pleasure to introduce Dr. Beth Sciaudone from NC State University. Beth is kind of hails from the Tar Heel State and has 3 degrees from the Triangle, although none is from my alma mater. So I'll just have to let that go. But she has bachelor's from Duke University, master's and PhD from North Carolina State University. And she's also well known outside academia for long-time involvement with the American Shore and Beach Preservation Association, ASBPA, which she is managing editor for the Shore and Beach Journal. So highly encourage students and colleagues to check out Shore and Beach. It's moving with the times and getting into resilience and many other pressing challenges we have. So another thing I'm super excited about introducing with Beth is her topic happens to cover one of my favorite stomping grounds in the Outer Banks. So I'll hand it off here and have Beth go ahead and jump into your talk. Thank you for coming.
Thanks so much, Tom. Thanks to all of you so much for having me here for this seminar series. As Tom said, I'm a research assistant professor at NC State in the Department of Civil Construction and Environmental Engineering. And my talk today is about the resilience of coastal transportation systems in North Carolina. And so I think I'm going to go ahead and just turn off my camera so y'all can concentrate on the presentation, and then at the conclusion, when we have questions, I'll turn my camera back on and we can have questions and answers and talk about the presentation. So thank you. If I can figure out how to turn it off when I'm presenting, then I'll be doing really well. Okay, here we go. So this slide shows the outline or framework for the talk. First, I'm planning on reviewing some definitions, and then I will talk briefly about some available guidance for transportation resilience. And I will conclude with an overview of some of the work that we are doing at NC State on transportation system resilience in the case studies, focusing on NC-12, road and network analysis project, and some work with the ferry division. So I'll start with the definitions. I know many of you deal with this, that there are different definitions. People think of resilience in different ways. And so I wanted to put this definition out there. This is a definition developed by the Federal Highway Administration. It's similar to many of the other definitions since it reflects the ability to respond and recover from disruptions. So Federal Highway defines resilience as the ability to anticipate, prepare for, and adapt to changing conditions, and to withstand, respond to, and recover rapidly from disruptions. Now, we all think immediately about roads and bridges when we're thinking about coastal transportation systems, but I do also want to give a shout out to ferries, because North Carolina actually has the 2nd largest state-run ferry system in the United States, only after Washington State. So these are the 3 modes of coastal transportation systems I'm going to be highlighting today. I know all of you are very familiar with the types of hazards that might be faced by coastal transportation systems. I know near Old Dominion, there's constantly the issue of nuisance or sunny day flooding. There's always flooding associated with storms, wave run up, and overtopping impacts, wave forces on structures or roadways, erosion or scour, and always long-term ongoing shoreline retreat or recession. So I'd like to review some of the guidance that is currently available to address resilience and adaptation planning. These resources are primarily focused on transportation systems that I'm going to be talking about, but they can also be applicable to other planning situations. On the left-hand side, you see the Federal Highway Administration's Vulnerability Assessment and Adaptation Framework. In the middle, there's a document called Highways in the Coastal Environment, or HEC 25. And on the right-hand side, there's a document that is an implementation guide for nature-based solutions for coastal highway resilience. And all three of these publications are available online, and they are published by Federal Highway Administration. The Vulnerability Assessment and Adaptation Framework provides a step-by-step process to conduct a vulnerability assessment. So this is a methodology that can be used for any type of vulnerability assessment. The case studies and examples in the document are focused on transportation systems. The basic steps that this document goes through are collecting data, including information about what is vulnerable and what the hazard is, to assess vulnerability with stakeholder input and engineering input, evaluating adaptation alternatives, considering the criteria that is important to the community, as well as cost benefit and risk analysis. Finally, the last step would be to integrate that assessment into the decision-making process, including planning, project development, and design. So this document essentially provides a framework for those in the transportation space to conduct these vulnerability assessments. HEC 25 is a much more technical resource, including tools for planning, design, and operation of roads near the coast influenced by tides or waves constantly or occasionally. That includes policy background, a really nice comprehensive review of the principles of coastal science. I used to use an earlier iteration of this document actually when I taught an intro to coastal engineering class, and that would be towards the end of the class. And my class used to say, gosh, this document actually explains all of these concepts very well and very succinctly, better than almost our textbook does. So this is a very nice summary of the principles of coastal science and engineering. It also goes into design considerations for revetments, roads near shorelines with high rates of erosion or recession, bridges, and considerations for scour. And finally, it touches on some of the concepts that the vulnerability assessment and adaptation framework goes into detail on, including what is the risk, how do you assess vulnerability, and how do you approach adaptation. The third Federal Highways document, Nature-Based Solutions for Coastal Highway Resilience, provides needed documentation about how to consider nature-based strategies in the planning process and how to select appropriate nature-based solutions. Takes you through the process from planning and obtaining funding, engineering design considerations, permitting, construction issues, and finally, how to adaptively manage those nature-based solutions. This document actually also has some helpful technical fact sheets on different types of nature-based solutions that can be used in transportation, including marsh vegetation, marsh breakwaters, a marsh sill, beach nourishment, construction of pocket beaches, and dune restoration. So those are all nice sort of like pullouts that are available in this document. There are also two North Carolina specific documents that are related to coastal transportation resilience, including on the left, the North Carolina Climate Risk Assessment and Resilience Plan, and then the North Carolina DOT Resilience Strategy Report. Some highlights of these documents, I know this is a lot of text, but on the left, from the coastal infrastructure section of this North Carolina Climate Risk Assessment and Resilience Plan, they do state immediate focus must be on developing strategic priorities for public and natural infrastructure improvements, as well as actions that integrate climate resiliency into agency operations local disaster recovery programs, and long-term planning. And in the transportation section, it notes all modes of transportation must be assessed for resilience to build adaptive capacity and redundancy moving forward. And so as part of this process, NCDOT has developed their own resilience strategy, which lays out their roadmap to guide resilience decisions. And they are using this area concept, which stands for absorptive, restorative, equitable access, and adaptive capacity. So this roadmap includes policy, program, and practice decision-making with stakeholder input, with the aim to incorporate resilience in each phase of the transportation project delivery. So that's just to give you a little bit of background of kind of some of these resources and some of the framework under which some of these projects are being conducted in the state of North Carolina. And again, the projects that I'm involved with are just a tiny subset of the things that NCDOT is doing and others in the transportation resilience space in North Carolina. So now I'm going to move into giving some detail on some of these case studies, with the first one being NC12. This is the project that I've been working on for most of my time as a research assistant professor here at NC State. NC12 on P Island has had an ongoing coastal monitoring program in place since 2011. And the aims of this program are listed here: to monitor and identify vulnerable areas of P Island now and in the future, to inform planning for future phases of what's called the NC12 Transportation Management Plan. So this is a phased approach to maintaining a transportation corridor along this section of NC12 from basically from Oregon Inlet down to the town of Rodanthe. And I'll show y'all a map in just a moment. And in addition to that, this project also is designed to meet requirements of the 2012 U.S. Fish and Wildlife Service easement, which allows this road to be maintained through the P Island National Wildlife Refuge. And in addition, there is a terminal groin structure at the northern end of the island. And so if you are more interested in details of this project after this presentation, we do have our annual reports available on NCDOT Connect. And there's also a published journal article, which is highlighted here at the bottom of the page, called Vulnerability Indicators for Coastal Roadways based on Barrier Island Morphology and Shoreline Change Predictions. And that was published last year in Natural Hazards Review. So just to show you where the study area is located, I know most of y'all probably in Virginia. P Island is at the northern tip of Hatteras Island, shown here in this map on the left. We have developed a system of shore perpendicular transects spaced 150 feet apart. The northernmost and the southernmost transects are shown on this location map. At present, to assess vulnerability in this area, we're using 3 primary indicators. The first one, island width, is the distance from the sound side or estuarine shoreline to the ocean shoreline. And for this, we are using a threshold value of 1,000 feet. The reason we are using 1,000 feet is because the sections of the island that were breached during Hurricane Irene in 2011 were just under 1,000 feet. So that's where that number comes from. The dune crest elevation of above the road is the next vulnerability indicator. And we are saying our threshold there, any dune crest elevation that is less than 10 feet above the road is a vulnerable transect. And this is based on some numerical modeling that was done by Marjorie Overton and John Fisher years ago. And this vulnerability indicator basically assesses vulnerability to storm impacts, whereas island width would be also storm impacts, but more of a vulnerability to breaching. And then the final one, the critical buffer, which is a distance of 230 feet from the edge of pavement. Anytime the ocean shoreline is within 230 feet or less of the road edge of pavement, then we are calling that vulnerable. And this indicator has an interesting history. This was actually developed by a master's student years ago who evaluated NCDOT's records and learned that back in those days, DOT would move the road landward regularly. And so that decision to move the road landward was made essentially on average when the edge of pavement, when the shoreline was within 230 feet of the edge of pavement. And so this indicator takes into account long-term erosion. We use aerial photos as well as photogrammetry derived digital terrain models to evaluate each of these indicators at each of the transects across the study area. This is a figure from that paper and shows how these measurements are made. So the island width is simply calculated as a distance from the ocean to the estuarine shoreline. And then if we project that transect from the edge of pavement to the ocean shoreline in the cross section, we extract the dune crest, which is maximum elevation between the edge of pavement and the ocean shoreline. And then the distance from edge of pavement to the shoreline is a simple measurement. So we're doing this 4 to 6 times per year using GIS techniques. We also compute a long-term erosion rate using older shorelines. We go back to the date when the terminal groin was installed, which was late 80s, early 90s by the time it was finished for the northern 5 miles of the study area. And we go back all the way to the 1940s shorelines for the southern portion of the study area. But each year we do add the additional shorelines, which are usually 6, sometimes as few as 4, that are added each year, and then we recompute the erosion rates. And so these erosion rates are used to make improved estimates of what the island shape may look like in the future. And as I'll mention, we do project to 2 future planning horizons, 2030 and 2060. And the last time we talked about this last week, everybody mentioned, gosh, 2030 is getting here pretty quickly. So that's a near-term planning horizon. So you can see here, the transects line up with the location of the erosion rate. And here at the very most northern part, there's accretion in the long term. And that for the most part is because this terminal groin was constructed, because this island was migrating to the south. Terminal groin was constructed and reduced erosion in this area, and it caused accretion in the groin pocket. And then there's erosion for the most part across most of the study area. There's a small area of accretion in this area right here, which is what in this project many times we refer to as kind of the stable zone, because the road in this area is relatively far away from the shoreline. There's still a well-developed dune field here. And then we go towards the town of Rodanthe, which is about right here. And then the rates of erosion are quite high in the town. Each year we present an annual report and we include each of the indicator vulnerability assessments for each of the dates. And so let me walk you through this figure a little bit. So here at the north end, we have the terminal groin. Down here at the south, we have the town of Rodanthe. And we sort of have identified each of the reaches by name. So this, many of you may be familiar with this area. So this northern area has been called the canal zone for quite some time. We have the next reach called the North Pond, meaning these managed wetlands. These are managed by the U.S. Fish and Wildlife Service, and they control water levels and such, depending on which birds are in the area at the time. This next area is known as the Old Sandbag area, presume this again is a name that's been around for quite some time, presumably because there used to be sandbags there. And then New Inlet. I also recently heard that this New Inlet area is also known as Split Pea, which I kind of like because, you know, Split Pea Island. So that's kind of fun. In this New Inlet area, there was a breach that occurred during Hurricane Irene back in 2011. And this blue that you see here is an interim bridge, which is a short-term, relatively speaking, shorter-term solution to some of the vulnerability in this area. Then what I just told you is kind of the stable zone. And then the S curves area, which is quite vulnerable just north of the town of Rodanthe. And so each of the indicators is shown for each of the dates. This particular graph is for 2021. So we have February, April, June, August, and September. And anytime you see black, that means at that transect, the transect was determined to be vulnerable according to that indicator. So there's several different areas where the island width is narrow and the vulnerability trigger or threshold is exceeded for island width. Right here, it's hard to see, but there are some small ponds that are hydraulically connected to the sound. And so in that area, we measure the distance from those ponds to the shoreline because we're counting that as the estuarine side shoreline because it is hydraulically connected to the sound. So that's why those are small, even though it might look like in this figure that that area is wider. The dune crest being below 10 feet above the road occurs very regularly across the whole study area, with the exception of the stable zone. And then the critical buffer, which is where the shoreline is within 230 feet of the road. Those areas are mainly concentrated in the canal zone. In the ponds area, there's a Pea Island Visitor Center. Some of you may have been there right around here. So this area is kind of right in front of the Pea Island Visitor Center. And then towards the S-curves north of Rodanthe area. And so this just shows each indicator where those are exceeding their thresholds, and then the composite shows where the green is where no indicators are met. The yellow is where one is, and then the orange is where two are, and then red would be where all three are actually being exceeded. We also use the shoreline erosion rates and a prediction interval to forecast the potential range of shoreline positions in 2030 and 2060 and assess where the road and shoreline, where the shoreline will lie within the 230-foot buffer. And so this slide shows the forecast vulnerability as of 2030. This highlighted portion here is the interim bridge. And then most of you may be familiar with the fact that here in Rodanthe, they have recently completed another bridge, which is commonly known as the Jug Handle Bridge or the Rodanthe Bridge. This figure is from 2021, so the bridge wasn't quite open yet, but I've shown it here in a dashed line. And so you can see this Rodanthe Bridge is adapting to the vulnerability of this particular section, but there are other vulnerable sections of the road shown further north. And then with the shoreline forecast to 2060, those vulnerable sections get longer. There's more vulnerability just south of the interim bridge. And again, this area that is bypassed by the Rodanthe Bridge. So in addition to the monitoring, we do have ongoing research in our department. This particular figure with all these abbreviations was created by a recent master's graduate. His name is Adam Baer. So in addition to the 3 vulnerability indicators I was talking about that are our primary ones, there are also lots of other things that could potentially be predicting vulnerability. So Adam tried to come up with a list of pretty much anything that we could measure with the data sets that we have. and that might be an indicator of vulnerability. And so this figure kind of shows all of those. There were 14 different things he considered, and they're listed here. Anything the things we're already using: island width, dune crest height above the road, edge of pavement to ocean shore. But then we also added other things like edge of pavement to estuary shore, dune toe, kind of like cross-sectional area, or what we're calling volume per length. Lots of other things: beach slope, shore orientation, road elevation, and such. And Adam, spoiler alert, Adam did graduate and got his research published. And this is all described in this paper here. Effectiveness of indicators for assessing the vulnerability of barrier island highways. And that came out earlier this year in Transportation Research Part D, Transport and the Environment. So Adam pulled all of these different potential vulnerability indicators at each of our transects, and then considered impact from storms. So Adam tested these indicators primarily with storm impacts, not so much with any kind of long-term erosion impacts. So Adam assembled this database of 7 storms. Most of them were hurricanes, but there were 2 nor'easter winter storms. And the way that Adam selected these storms were essentially because we had imagery and topography available both pre and post storm. So he could determine all of the indicators and whether or not the road was impacted by the particular storm. And you can see on the right-hand side the tracks of some of these storms. And then, of course, we don't track the winter storms as well, as far as you can't, don't have a specific track of the eye of a winter storm, but both of those winter storms impacted the study area for a number of days. So this gives an example of how Adam determined the locations where the road was impacted. And this provides a proxy for roadway impacts. So essentially, Adam looked at the aerial photos and said, okay, is there overwash sand on the road? And the rule he used to digitize locations that were impacted by overwash was, okay, there's half of the road, 50% of the road is covered with sand. He also observed areas where we had oceanside erosion and scour and damaged pavement, for example, as shown in this panel B. And that was sometimes hard to verify. So he did check that with the on-the-ground engineers at NCDOT to make sure his assessment was accurate. And then, of course, it was quite obvious anytime there was breaching damaging the road. And really the only time that occurred in his data set was during Hurricane Irene in August 2011. Overwash was the type of storm impact that occurred the most frequently. So if you're really interested in this, I would encourage you to check out Adam's paper. But as a summary, I included this. At the top, we have a confusion matrix. And this is basically the way that Adam approached the classification problem. Like he's checking to see, okay, did this indicator predict that the transect would be impacted by the storm? That would be predicted vulnerable. And then if it was actually impacted by the storm, then it would be observed vulnerable, and that would be a true positive. And if the indicator predicted that that transect wasn't going to be vulnerable during that storm, and it also was observed to not be vulnerable, that would be a true negative. And the other combinations would be like, okay, we predicted that this would be vulnerable, but there was no impact. It was not observed to be vulnerable. That would be a false positive. Or we predicted that it wasn't vulnerable, but it actually was impacted. So that would be a false negative. And so these different types of metrics can be used to compare the predictions and observational data and two metrics that are used to quantify the skill of each of the indicators and be able to compare them that Adam used were precision and recall, where precision is a measure of how many of the positive predictions made are correct. So that's the true positives. And then recall is a measure of how many of the positive cases the classifier correctly predicted over all the positive cases in the data. And this F1 score, you see the equation here. It's a pretty simple equation. TP is true positive, FP is false positive, FN is false negative. And you can also plot these things, recall and precision, and then you have something called the precision recall curve, and that's for different values of the threshold of the indicator. And so it kind of considers, like, no matter what you consider the threshold to be, how good of an indicator is this? And that's measured by the area under the precision recall curve. And so these are kind of the ways that Adam evaluated each of the indicators to see whether they were effective at predicting vulnerability. And so this table, it shows all of the indicators examined on the left-hand side. These were the optimal thresholds for maximizing the F1 score. And then the max F1 score. And then the area under the precision recall curve is how he used to rank all of the indicators by how skilled they are. And the one that turned out to be the most skilled in Adam's research was the edge of pavement to the dune toe. So that actually makes some sense, that for storms, the buffer distance between the pavement and the dune toe is a better indicator than the edge of pavement to ocean shore, which is what we use generally in the program, which is third effective here. But being that these are storms, you might expect that the water level would be almost to the dune toe. And so maybe that's why this is more effective for storm impacts. I want to point out that island width is down here as unskilled, but we don't think that that was actually fairly assessed by this data set, because only one of the storms caused breaching. And so because we're trying to capture capture the risk or the vulnerability to breaching with that indicator in the main program, and the data set was very limited, we don't think that island width necessarily was fairly assessed by this particular set of storms. So moving into another student project on adaptation, as many of you may already know, there is a phased approach to kind of different projects being done out on NC-12 to maintain this transportation corridor. And the first, well, not counting the interim bridge, the first adaptation effort that's being put in place is this Rodanthe jug handle bridge. And this is sort of a close-up showing our projected 2060 shoreline, which is a solid blue line here. And then the prediction interval, which is sort of capturing the uncertainty in that prediction. And then we have the location of the bridge, which is now open. And then the area that's predicted vulnerable as of 2060. So just to give you sort of an idea of what that looks like right now. I wanted to point out, and many of you again may already be aware, that there have been quite a few storms this fall that have already caused overwash in this particular area. This is a great photo. If you all want to get some great Outer Banks photos, I definitely suggest following Epic Shutter on social media, because they have some amazing shots. And in this one, you see this picture's from September 10th. So you can see where the road previously was, all the sand and overwash that's happening in that location. And then these are some sandbags that are still there. And so right now NCDOT is working on removing the sandbags and removing the asphalt and everything out of this area. And if you were on earlier, they are like, due to all these events, this has been quite a challenging project for them. So you can kind of see in this photo that Rodanthe Bridge around in the sound side. Here's another great photo from Epic Shutter. This was taken October 12th, and you can see them working on pulling out the asphalt and sandbags and such. And all of this that they had to push off the road happened in these prior storms. You can see all that sand accumulation, and there have been a couple great pictures of these road signs almost to the ground, showing how much sand has actually been accumulated there. So I have a current master's student who's sort of asking the question, you know, what are some of the potential outcomes that could be happening here? And she's using an X-Beach model, calibrating it with Hurricane Sandy, and she's going to be validating it with some other storms and working on modeling some other scenarios. Initially, she did some preliminary work, applying some expected sea level rise to a Hurricane Sandy to predict. So once that road is gone and they're kind of allowing this area to evolve, you know, what may happen in terms of location and extent of overwash in a Sandy-like storm with different levels of sea level rise. So that's kind of some exploratory initial work that she did. And she presented a poster on this in September at the ASBPA conference in Long Beach. And so her preliminary results from this is that her X-Beach model is adequately simulating dune erosion and overwash due to Sandy with a skill score of 0.61, which is, I think, very good. And she also showed here some figures where she has Sandy under no sea level rise, what happened, and you can see deposition is sort of the orange to green, and then erosion is the light to dark blue. So some deposition and overwash here in this area. And then if she adds 0.2 meters of sea level rise, that increases, and then 0.5 meter of sea level rise increases it even further. So not shocking results that sea level rise would be expected to increase the overwash extent, and overwash extent and elevation also increase with a higher sea level. I want to highlight quickly another project that kind of has just started, a road network analysis project. The aim of this project, which I'm working on with two different PIs. The main lead PI of this project is Dr. Evan Goldstein at UNC Greensboro. Some of you may know him for the network analysis piece. And then my colleague, Catherine Anardi, Dr. Catherine Anardi here is leading the fieldwork component. Basic idea in this project is that there's a road network. It's modeled with each intersection as a node, and each road connects those nodes. So you can kind of see that here on this image. And down here, what you can kind of see in a side view is what that road network might look like with elevation considered, and then a potential flood level. So the aim here is trying to look at how can network analysis help us figure out how to design or build more resilient transportation systems. And so what Dr. Goldstein is doing in a model is looking at all these nodes, considering the nodes and removing them in order of elevation, such that it would be like, okay, so we've got a water level rising, and then we're going to remove those nodes in order of elevation. And as you do that, there becomes a time when there's a critical node that's removed, and then essentially the road network is no longer serving the appropriate connectivity purpose. So in this particular case, that red node is shown right here. And so once that node is removed, then the network is severely fragmented. And Dr. Goldstein and colleagues have published this work in this paper, Thresholds and Road Network Functioning on U.S. Atlantic and Gulf Barrier Islands. So they did this, all of these models of every Gulf and Atlantic barrier island, and they figured out what is the critical node on each of these islands and what is the elevation of that critical node. And then they looked at, okay, that elevation, what water level return period event would that elevation be flooded by? And turns out 61% of the critical nodes are flooded by 1 in 100-year events. 35 of those critical nodes are flooded by 1 in 10-year events. And you can see up here in the study area we've been talking about that those critical nodes would be impacted by a less than 10-year storm. And we definitely see this because as you saw in the previous couple slides, there are sections of these roads that are impacted or closed, more than once a year. So the piece of the project that I'm working on with Dr. Goldstein, Dr. Nardi, is testing this network model that Dr. Goldstein and colleagues developed, testing this with real world observations. So be comparing the model results with reported closures from the North Carolina DOT's Traveler Information Management System, drive.nc.gov. Many of you may be familiar with it. It's very nice. It has traffic cameras, and they do document anytime any roadway is closed or hazardous or there's construction. So it's possible to pull out previous event data and where what sections of the road were closed. So that's going to be compared with Dr. Goldstein's model. And in addition, Dr. Nardi's team is working on developing and deploying machine learning enabled cameras at critical intersections where maybe the drive.nc.gov cameras are not available. And they'll be measuring the flood events there. And so this is kind of what they might look like. And then these pictures are from the training of the machine learning. So trying to be developing the software such that the flooding detection takes place automatically. So this is sort of like training the machine learning algorithm to recognize where the flooding is actually occurring. And so that project's underway. So I'll keep everyone posted on how that goes. And then the final project that we are getting started with is with the ferry division. And we are conducting a statewide assessment of the vulnerability of the ferry systems facilities. And the aims and scope of the study are shown here. This is kind of directly from the proposal, and you see some impacts there on the right-hand side from Hurricane Florence at the Pamlico River Ferry Division facility. So our aims and scope for this will be assessing the vulnerability of all of the ferry division's infrastructure assets with respect to natural hazards. And we're going to be doing that at present and then forecast to the 2040 and 2060 planning horizons. Then to assess the condition of ferry channels at present, as well as potential climate impacts. Then to prioritize assets for adaptation measures where needed. And finally, to provide recommendations on potential adaptation options and potential timeframes for implementation as well. We framed this particular study using the Federal Highway Administration's Vulnerability Assessment and Adaptation Framework. And this figure is right out of that. And as I already sort of discussed, we'll be taking these steps, setting the objectives, compiling data, assessing vulnerability, analyzing adaptation options, and incorporating results into decision-making. The research team is planning on using climate and hazard data along with asset information to identify and evaluate the exposure, sensitivity, and adaptive capacity of the ferry system. We're going to plan on assigning a level of risk to each portion of the ferry system, and this will include the probability that an asset will experience an impact and the severity of that impact. And again, we'll be considering not only current but projected conditions at the 2040 and 2060 planning horizons. And the hazards we're looking at: storm surge, sea level rise, shoreline change, channel shoaling, wildfire, and perhaps others. We're currently working on a best practices inlet review report where we are making some modifications potentially to our scope. And as I mentioned initially, we proposed to focus primarily on natural hazards. But the Ferry Division has actually asked us to also try to consider some of the social equity pieces of this as well. So I'm hoping to learn a lot from the colleagues here at Old Dominion about that social vulnerability, social equity analysis as well. So to conclude, there are many agency resources available for resilience planning in the transportation space. Don't need to tell all of you that coastal hazards are ongoing and some of them are likely to worsen with climate change. And just wanted to give an overview of our ongoing research, which is aiming to inform those planning efforts for resilience and adaptation. So thank you so much, and I would be happy to take any questions.
Thank you, Beth, and thanks everyone. Yeah, we've got a couple minutes for some questions. You can raise your hand, jump right in and unmute, or drop a question if you'd like me to ask in the chat. Beautiful sunset there, by the way.
I wish this is from Flickr, Dirtman's Images, also another source of some great Outer Banks imagery.
I want to say that's Southern Outer Banks, but
this is Silver Lake on Ocracoke.
Ocracoke it is.
Yeah.
Right.
Because it's got a ferry, so I like that.
Oh yeah,
Ferry.
can't go wrong. Have we got anybody in the chat?
Can I ask a question, Tom?
Go ahead, yes.
So Beth, at what point do you just say we can't afford to do the mitigation anymore? I mean, the Rodanthe Bridge must have cost a small fortune or a large fortune. And so at what point do you just say we're not going to do this anymore?
You know, I mean, that's something that you know, DOT is certainly thinking about. Like I said, they think about, I think, this corridor in sort of like a phase sort of way. As you probably know, there was a talk years ago of a 13-mile bridge that went all the way down from and completely bypassed this section of the refuge. You know, it's hard. It's because I am presenting to DOT kind of like, here's the vulnerability, and then DOT has to take that information and make planning decisions. And some of the things they say is that, you know, clearly, you know, there are things that that need to be done and additional analyses, but they have a certain way of prioritizing their projects, and the way that's done right now, I think has a lot to do with like the number of people that are on individual roads and like accidents and such. And so I think even though there are a lot of visitors that travel on this road, and it is a very critical route. I mean, the criticality is very high because there's no other escape route. There's no other way for people to get medical attention and such like that, unless, you know, they're in a helicopter or whatever, an emergency situation. But I think, yeah, it's hard for me to answer that question since I don't directly work for DOT. It's definitely on everyone, you know, obviously it's like the poster child for sea level rise, climate impacts to a road, and coastal hazards. So certainly something that, you know, they're thinking about in the long term. What's the best way to maintain transportation service to those who live in the southern part of that area?
No, it just, I always wonder, at what point do you just say we have to just abandon this and move everybody and let this go back to nature kind of thing? But I don't expect you to answer that.
Yeah, and I mean, there's lots of social vulnerability questions associated with that I'm definitely not equipped to answer. But there were so many interesting talks at that recent conference that kind of ODU had an important role in planning. Like, and if people, I think those are all recorded too. So if people didn't get a chance to attend those, I definitely recommend it. And I feel like those Louisiana discussions also so interesting, and a lot of these same kinds of concerns and issues about, you know, how long can people maintain these communities and such. So yeah.
Thank you.
Thanks.
Yeah.
Hey, I think John might have a question.
Yeah, hi, Beth. The traditional solution is to pump sand back onto the dune field and so forth. I guess this is similar to Eileen's question, is that a viable solution? I mean, could that be a way to sort of re-engineer parts of the island that are particularly thin or vulnerable? Or is the solution just not long lasting enough to make it worth the effort?
That's also a great question. I mean, part of the reason I think it's so sensitive in this area is because it is a national wildlife refuge.
Mm-hmm.
And so I think they do want to minimize, you know, the number of bulldozers and pumps and all of that is out there. And so that's, I think, one of the reasons, in addition to it being kind of a one-time build and you're done, but when they put the Rodanthe Bridge in, then they are, like I said, removing the road and the sandbags, and they are going to sort of let that section evolve, and we'll see, you know, is what's going to be happening there will be sort of like a living lab for, you know, potential adaptation alternatives. I mean, I think if you're in a highly populated area, and the economics make sense to pump sand and build dunes, in my personal opinion, I do think it works, and certainly in the short term with current rates of sea level rise. I mean, that's what many places are currently doing. But this particular area, I think, is more sensitive because of the refuge that they're not like they're eager to kind of allow that to evolve and sort of see what happens and whether, you know, it's interesting. Some of these overwash fans are very good bird habitat. I've learned that from my biology colleagues at the refuge. And so, you know, when overwash fans happen naturally, then the birds and the turtles love those. So
yeah, I guess it's difficult to decide what your real criteria are. You know, is the transportation the most critical thing, or is the natural habitat something that is critical to preserve? So I understand the difficulty of making those decisions. So anyway, thank you for your answer, Beth.
Yeah, thank you for the question. I do see one in the chat where someone asked, the student projects were so inspiring. Could you share a bit of how the students choose their projects? Sure, I'm happy to do that. So working with students is one of the most fun things, and I'm sure my colleagues at Old Dominion will agree. It's kind of a combination. So my student who's working in the Rodanthe area really wanted to learn X-Beach and figure out, you know, how to build an X-Beach model, how to do that, you know, for future work as a consultant and such. And so that ties in really well, I think, with the fact that we have a lot of data in that area, and you know, it's something that we're kind of working on with the ongoing monitoring. So that kind of was sort of like a process of like, oh, you know, I want to learn X-Beach. Oh, what are some interesting questions we could ask? You know, what can we explore sort of with the X-Beach model, how the land cover might be changing potentially within the near term with storm impacts using an X-Beach model. So that's how she picked that. Adam, I will admit, he and I were just kind of, I truly wanted to know what other input, what other indicators might be better than what we're currently using. How could we adjust or modify? And so I just sort of presented that question to him, and he came up with sort of the approach and what are, when we kind of brainstormed, what are the many different kinds of indicators that we could potentially use, between the he did literature review, what other people are using and such. So yeah, it's been fun working with students. I actually have an undergraduate student right now who's working on the ferry project, and she's doing a big literature review, trying to figure out, what are the most important hazards that have been looked at in other ferry projects. And so yeah, kind of just a combination of what are the ongoing research projects and what are your interests.
Hey, great.
Tom?
Yeah, Jim.
Yeah, I did, for my dissertation, I did a shoreline study similar to what you're doing for the eastern shore of Virginia. And one of the questions I kept getting was, how do you know where the shoreline is? I mean, is it breaking waves, wetted sand, et cetera, et cetera? But the issue, I guess the answer I gave was, well, you still have the uncertainties of the imagery itself. I assume you used aerial
Yes.
photography and not having somebody go out and walk the shore.
Yes. Yeah, we're wet, dry, Dolan. Yes.
But over time, I guess as long as you're consistent, it seems that error would sort of go away or become less important.
I mean, that's why we use the prediction interval band. Yes, there certainly is some uncertainty, both associated with the, I do think the photography is pretty decently accurate. It's a 2.5 foot pixel size. And then we have, but there is uncertainty with the water level and the wetted sand. We do have the photos taken as close to high tide as they can. But yes, there's certainly uncertainty in the shoreline positions, but we do have a long-term database and multiple shorelines per year. So we're doing a linear regression to get those erosion rates. So we're hoping that kind of it all, it's certainly still there, but we're hoping that we're still able to capture the long-term trends.
Okay, thank you.
I'm not seeing another in the chat. But I think, Beth, you've just given the best plug possible for my coastal GIS class.
Awesome.
In the spring. So an offer stands if the ODU Hydrone can chip in with nearshore bathy or something, just give a holler. More than happy to take a crew down Outer Banks. Anybody else? Not hearing so. Again, a great big thanks to Dr. Sciaudone and everybody for joining us. If someone needs to catch this later, you have a colleague who couldn't make it today, we can reach out and we can relay the recording. And next week, Eileen, I think we have one more.
Yes, one more next week. Tara Mazzini from VIMS. Yes.
Okay. So thanks again, Beth, and thanks everybody. Y'all have a great week.
Thank you so much for having me. I appreciate it. Take care.
Most welcome. Bye-bye.